All right, there are three laws that we're going to talk about today, and they deal with the volume, temperature, and number of moles. And this is a relationship of how gases interact under these different types of conditions. You will not have to remember the names of the people, which is nice. So there's Charles' law, Boyle's law, and Avogadro's law, but don't worry about the laws. Just know how to use the equations and what variables you're given. So when we talk about Charles' law, it's a temperature-volume relationship. In other words, we talked yesterday very briefly about, remember the box with the ping pong balls in it? That as the temperature goes up, what happens to the ping pong balls? They're moving faster. So as the temperature goes up, what would you guess would happen to the volume of a gas? It would get bigger. And as the temperature gets cooler, or the temperature decreases, then the volume of that gas decreases. And some of you may have experienced this in the winter. The first time I noticed it actually is with my son when we bought a balloon for some birthday party, the Mylar balloon. It was like in the dead of winter in January. We went in the store, we bought the balloon with the helium inside the Mylar balloon. As we're walking outside to the car, my son points out, he goes, "Dad, it's losing the air." He's only 3. He's like, "Dad, it's losing the air." And I'm like, no, that's Charles' law. He's like, "What?" Okay, don't worry about it. And as soon as we got in the car and warmed up the car, the balloon went again. But as soon as we got out of the car to go into the house, the balloon went, it started to shrink up again. Because the temperature, as the temperature gets lower, those gas particles aren't moving around as quickly. So the volume of the gas decreases. And I have a graphic in your notes that actually shows a relationship that we can determine what absolute zero is based on if we were to track the volume of a gas in relationship to the temperature, and it actually comes out to around -273. But one important thing that we have to remember when we're working with Charles' law or temperature, when we're working with gases, is that we want to convert it to kelvins. We did that yesterday in the homework. Because if we get below zero, which is not too difficult to do here on Earth, I mean, once water freezes at zero and we get below that, now we have a negative value. A negative degrees Celsius would give us a negative volume. That's bad. But if you use kelvins, we're always going to have a positive volume. So this is a direct relationship. As the temperature goes up, so does the volume. Temperature goes down, so does the volume. All right. I will do these demonstrations after we get done with working out the different types of math. I actually have them set up over here, so don't freak out on that. Here is a graphic that I stole from somewhere on the internet. This is it's like a tanker car for a train where they transport some liquids. This is, I can't remember what the thickness of the wall was on that. I think it was at least 2 or 3 inches. But what happened was, this was transporting some liquid. They emptied out the liquid. They asked some guys to go in and steam clean it. And obviously it was in the wintertime. So they went in and they were using the power washers that had steam, which obviously was warmer. But what they didn't do is they didn't leave the pressure valves open to allow air to go in and out. And that's part of one of the demos that I'm going to use, is like showing this, but on a pop can size scale. But what happened was they closed this whole tanker car up, and it was still warm inside while they were still cleaning, and when they left it was still warm. But eventually that gas or that water started to cool down. Well, what happens to the volume of a gas when it cools down? It gets smaller. In other words, the pressure also goes down. So what happened is, as it got cooler out, or cooler inside as well, that gas compressed, which disturbed the equilibrium, and the atmosphere just crushed this thing. So they came back and they saw that this tanker had been crushed. It looked like something had fallen on it. Well, that's the pressure of the atmosphere. So one thing that you want to make sure that you're doing is, if you're cleaning something like this, or you're heating something up that has a gas inside, make sure that air can either go in or out rather easily. One thing also, back when I was a kid, and they don't advise it anymore, is that if you know that a tornado's coming through your neighborhood, open the windows. I love that. Yeah, spend time, open all the windows. That's what we would always do in school. We were part of the tornado drills. Before we'd go in the hallway, we'd open every window. Why do you think they would do that? Yeah, so that the pressure inside out, theoretically, would be equalized. Well, as you're opening the windows and a tornado comes through, it's not going to matter if you're opening windows. That building's going to be trashed. So I always loved that. Kind of like also when we had to practice for nuclear bombs. Get under your desk. You'll be fine. You ever see videos for that?
Yeah.
Yeah, duck and cover. All right. So let's work out a couple of these problems here. Yeah, they had a warped sense of humor on how to prepare for certain things like that. I was a kid. I loved it. Yeah, if a nuclear bomb's going to go off, just get under your desk and cover your head. You'll be fine. All right. Here's our first problem. It says a sample gas occupies a volume of 100 centimeters cubed. That's a volume, centimeters cubed, at a temperature of 200 Kelvin. What volume would this gas occupy at a temperature of 150 Kelvin, and the pressure and the amount of gas do not change? All right. So here's one of the things that I would get used to, because next topic or next week, we're going to be dealing with not only volume and temperature, but also number of moles and pressure. So it's nice to identify these variables. So it says that we have a volume of 100 centimeters, so that's my initial volume. I'm going to call that V1. And it says that we're at a temperature of 200 Kelvin, so I'm going to call that my initial temperature, T1. It also asks, what is the volume that would change this gas if the temperature went to 150? So you're always going to have a before and after situation. Okay? And the way that this equation actually looks, and you'll be given this, so don't freak out. It'll be either V1 over T1 is equal to V2 over T2, or you will have T1 over V1 is equal to T2 over V2. So these are how those two equations could look. All right. What we want to make sure is we want to identify what variable it is that we're looking for, and we want to make sure it is on top or in the numerator. So we know V1, we know T1, we know T2. It's actually V2 that we're looking for. So which of these two expressions would we use? Top one. So this one, we're going to get out of there. All right, we don't need it. So we're going to use this guy. Okay? Now what we want to do is make sure that we want to rearrange the variables before we start plugging anybody in. So I know V1, T1, so these guys are going to stay put. I'm looking for V2, so what that means is I need to move T2, or multiply T2 on both sides. So now my equation looks like this, where I have V1, T2 over T1 is equal to V2. And that's the hardest part of this whole problem, is rearranging the variables. Because once you've rearranged the variables, now we just plug the values in. So my V1, and that's one reason why I put the variables over the values, so I don't do something dumb and like say that that's T1 and that's T2. So then I can just go, okay, my volume is 100 centimeters cubed. My finishing temperature is 150 Kelvin. And my starting temperature was 200. And what is my unit for this? Centimeters cubed, because again, my Kelvin cancel out. So I have centimeters cubed and whatever that equals. What is that, like 75? Okay. Okay. So really, when looking at a question like this, first of all, identify your variables in the problem, just write it above, and then rearrange the variables, plug it in, piece of cake. Yeah, it is. So let's look at the next practice problem. We might need that, so let's just put it over here. Look, sorry, down there. Nope. Ah, shoot, just throw it away. Come on, go. Number 7 says if a sample gas occupies a volume of, so we have a volume, V1, 0.325 liters at a temperature, T1, of 30 degrees. Make that a T. What temperature, so question mark, T2, will the gas be if the volume is changed to 200 milliliters? So there's V2. So we do need that equation, don't we? So let's bring you back down. You think I enjoy playing with this too much? Yeah. Okay, so we will use this equation versus the other one because we're looking for T2. So what we want to do is move V2 or multiply V2 on both sides. So now my equation looks like this, where we have T1 V2 divided by V1 is equal to T2. What do we need to do? We have a temperature that's in degrees Celsius. You got to get that to Kelvin. So don't forget, because again, even though that's a positive value, every once in a while that could be a negative degrees Celsius. So you have to change degrees Celsius regardless if it's positive. Okay? So make sure that we do 30 plus 273. So what is that? 303 Kelvin. Okay? So make sure you check that before you start throwing values in. So my initial temperature, actually my only temperature, is 303 Kelvin. My second volume is 200 milliliters. Okay. We have milliliters and liters. What do you want to change? The liters or milliliters? Liters? Okay. So when you look at liters, how many milliliters in a liter? 1,000. Good. So it's 0.3. Whoop. 325. Thank you. Let's go the other way. So we have 325 milliliters. So we'll put our V2 is 200 over 325. What will my unit be for this?
Kelvin.
Kelvin, because it's temperature and the other two cancel out. And anybody get a number for that?
492.
192?
492.
492. Okay. I don't know. Is that not 492? Thanks, Alan. I'm recording.
186.
186? Oh, okay. 186. Close enough. Okay? 3 sig figs. So again, when you're looking at these questions, and again, we'll go through 3 different sets of these where it's a volume temperature relationship, it'll be a volume pressure relationship, and a number of moles and volume relationship. So just look at the variables. Identify them and say, ooh, I've got a V and I've got a T. I'm using that guy, or this guy, or that guy. Okay? All right. So let's look. And the 3s are part of your homework. The next one, Boyle's law. This is a pressure versus volume relationship. So as the pressure of a gas, and this graphic does a nice job of explaining it. And think about it, if you're in the hallways, you're a gas particle. Do you like walking through the hallway when nobody else is in the hallway, or do you like it when the whole school is in the hallway? Yeah, so that's the same thing. As we get more and more gas particles in the hallway, in other words, the area doesn't change or the volume doesn't change, it gets a little more compressed. Now think about if the hallways, what are they, about 10 feet wide? Let's say that we reduced it down to 5 feet wide because we need bigger classrooms. So now the volume is smaller. We have the same number of particles or same number of students in the hallway. It's going to get a little tight. You're going to be nudging each other a little more. You might even get squished. So as the volume gets smaller, you're bringing all those particles together. And if we compress this enough, we can actually change that gas into a liquid. But we won't do that in any of these problems because that's a whole nother ball of wax and set of problems. So as the pressure goes up, what happens to the volume? It goes down. So it's an inverse relationship. Where on the last one, temperature went up, so did the volume. So as the pressure goes down, what happens to the volume? It goes up. So it's inversely related. And is that our only? Yeah, we have 2 blanks there. And I apologize how small that equation is. The P1 V1 equals P2 V2. But we'll work with that here in a second. Does everybody have those 2 blanks? Okay. Decreases with increasing pressure. So again, and this is just another graphic, not too exciting. Is that all the blanks for that one? Okay, so let's look at these practice problems. All right, and your equation that you'll use for these is just one type of equation. Whoop, that's a 1. So the difference between the last set where we had a numerator and a denominator is because as one went up, so did the other. In this regard, the reason why we're multiplying both is because as one goes up, the other goes down, or vice versa. So that's why the equation looks like that versus the other one. But I like it like this because there's no two variables or two variations of this. So let's go ahead and look at the question. It says a sample gas has a volume. Let's move this out of the way. Sorry. Okay, so the question says a gas has a volume of 100 centimeters cubed when the pressure, so our initial pressure, is 150 kilopascals. What is the volume? Question mark. Yeah. When the pressure is increased to 200 kPa. Okay. You may notice that those numbers look very similar, but the units are different. All right. So let's see here. Which variable are we looking for? V2. So that means we need to divide P2 on both sides. So my equation now looks like this, where I have P1 V1 over P2 is equal to V2. And install. Let me scoot that down a little. Okay, so let's see here. So our P1 is 100 centimeters cubed, and our V1 is 150 kilopascals, and our final pressure is 200 kilopascals. What will the unit be for this? Centimeters cubed, and the number will be 75. So again, make sure that you rearrange the variables before you throw any numbers in there. We don't want to cross multiply. Okay. Number 9 says that a sample gas has a volume. So here we have V1 of 300 milliliters when the pressure, so P1, is 760 millimeters of mercury. What is the final pressure in atmospheres? What a nice guy. So P2, when the volume is changed to 5 liters. Oh man. So I gave you milliliters and liters. So again, what do you want to change? The liters or the milliliters?
Liters.
The liters? Okay. So if we have 5.5 liters, get that to milliliters. So that's 5,500 milliliters. Okay. And we'll do the atmospheres at the end. So again, you are given this. Which variable are we looking for? P2. So that means we're going to move V2 down. We're going to divide it on both sides. So my equation is P1 V1 over V2 with P2. And so now let's plug in. So P1 is 760 millimeters of mercury. And V1, 330 milliliters. And then 5,500 milliliters. And then, so how many millimeters of mercury is that?
46.
46?
45.
45.6. Okay. Now the question wants this in atmospheres. So let's oblige here. So 45.6 millimeters of mercury, and using the problem, okay, so we'll change from kilopascals to millimeters of mercury. And again, these are your, they're given to you, the variable. What is that? Oh my God, I'm drawing a blank. What is that? A conversion. There we go. Is it a conversion? I'm like, oh my God, I can't even think of it. So 0.009869. That's what happens when you get old. Don't get old, guys. Okay. And if you wanted to use the 101.325 kilopascals for 1 atmosphere, fantastic. That's fine. Anybody get a number for that? Should be small. I mean, it's only 45.6. You're going to make me do it, aren't you?
0.059.
What is it?
0.059.
0.059. Sounds good. Okay. And if you wanted to change this into atmospheres before you actually solve, that's fine. That is absolutely fine. Okay. All right. And let's look at the last set here. And the 4s are part of your homework. Avogadro. Okay. The last one before the demos.
Like guacamole.
Yeah, like guacamole. Now, Avogadro's principle deals with something that we've probably dealt with many times. If you blow up a balloon, okay, you're blowing air into the balloon. So if you're blowing air into the balloon, you're introducing more particles into the balloon. So what happens to the volume of the balloon? It gets bigger. So the greater number of moles, greater volume. If you let the air out of that balloon, what's going to happen to the volume? It's going to go down. Okay, so it's a direct relationship. As the volume increases, so does the number of moles. As the volume decreases, so is the number of moles. That one's pretty straightforward. And the equation looks like that. Don't be excited. I know you can't see it from there. But here are the equations that we'll be using for, I think, a quiz sometime next week. So this is Dalton's law of partial pressures, which we talked about yesterday, or the last time that we met. And Charles' law, Boyle's law, and Avogadro's principle. So let's do this one practice problem. Let's do it. A sample of hydrogen gas has a volume, whoops, wrong color, has a volume of 630 centimeters cubed. When the same sample contains 3 moles, that would be N1. Now again, remember, have we talked about number of moles? N? I don't remember doing that. Okay. N, for whatever reason, they use N as the number of moles. I didn't make up the rules, sorry. So it asks, what is the volume? Oops, so question mark. What is V2 in centimeters cubed? So we don't have to change that. When the sample is reduced to 1.75 moles, and the temperature and the pressure don't change. Okay, so here's how this equation could look. We could have either N1 over V1 is equal to N2 over V2, or you could have V1 over N1 is equal to V2 over N2. Okay? Which of these equations should we use? This one or the second one? The one that has the V on top. So this guy, get out of here. All right, so we're going to use that one, because we have volume on top. That's what our variable that we're looking for is. And that's one thing I like about identifying the variables, because then we can look at the equation and go, oh yeah, this guy we need to keep. Okay. All right, so we are looking for V2, which means that we need to multiply N2 on both sides. So my equation looks like this. V1 N2 over N1 is equal to V2. And do we have to convert anybody? I'm a nice guy. So our volume is 630 centimeters cubed. N2, 1.75 moles. And again, that's one reason why you want to put the variables there, so you don't accidentally go, oh yeah, 3 was the first one that I saw, so I'm going to put it there. Don't do that. And then 3 moles. So whatever double 630 is. So 1260. Is that right? Oh, that's not double. Sorry. Making the wrong math. What is it? 367. 368. Okay. Yeah, I was thinking wrong math there. Okay. So honestly, this isn't difficult. It's just a matter of looking at the question, identifying the variables, and then deciding which equation am I going to use. Am I going to use... Obviously, you're not going to use any of these today, okay? But on the quiz, obviously you would. All right, demo time.
Yeah.
about to demonstrate deal with Charles' Law. And this can has been sitting in really hot water for a while. Get out. Really hot.
Craig, do we have gloves?
All right, so that's part of being next to it. All right, so what I'm doing is I'm heating up the gas inside the can, and you can see that it's really getting excited. This I had some ice in, took it out, so it's a little cooler. So the gas inside is actually pretty warm. Would you agree? Okay. So if I take this and I place it in the cooler water, what's going to happen to the temperature of the gas inside? It's going to cool, which is going to cause the can to do what? Crush. So.
Whoa.
Wow. That was ice. Like crap. But I'm going to remove it for a moment without burning myself. Key is not to burn yourself. Trying to go fast here. Shut up. This will be, yes, it is very hot. It's coming off. There we go. Got it. All right. So obviously you can tell it's very warm. Another thing, warm, hot, whatever. Actually, this is starting to get a little excited there. So what I'm going to ask you is, let's put that in there, since I haven't learned my lesson. The particles are the gas that's in the can. There are some gases in there, because you can tell, because you can hear the can dancing. Okay. So are the particles in there moving around pretty quickly or not?
Yes.
All right. Now, this goes fast. Okay. So don't. Can you see here? Oh, sorry. Yeah. All right. So again, this is our atmosphere that we're experiencing right now. Woo! Wasn't that exciting? All right, this is an example of a multi-view shot. And what we can do with these multi-view shots is we can edit these so that we can get one of the best views. Maybe one view doesn't work out really well, but the other camera on here is I've got two round bottom flasks that are heated up, and I've got some water with some food coloring in there, and we're going to do a pretty cool demo here. This is a gas property, or a nice little demo to help demonstrate what happens when you take a very hot gas, and I don't know if you can see the steam that's coming off of here. Try to get a dark background here. I don't know if you can see the steam that's coming off from behind there, okay, from that camera, or if you can see it from behind that camera. So there's a lot of steam coming out of these round bottom flasks, and they're really hot, ready to go. If I had these without these openings here, these things would blow up because the pressure would get so great within. But what I'm going to do with this big one here so I don't accidentally knock it off, set it right there for just a moment. And we're going to focus on this small one. And what's nice is this is also going to give us some editing capabilities we can discuss. You can look at the raw footage and then notice how I edit some of this information out. All right, so here, what I want to explain is we've got water. That's a liquid that's boiling. In other words, it's changing from a liquid to a gas. As it changes to a gas, that gas is being heated inside of the round bottom flask as well. As it's being heated, it's building up pressure, a lot of pressure. I mean, it's pushing quite a bit. I don't know if I can get a piece of paper to kind of demonstrate. So I'm not going to put my hand on it, but it makes a nice little hissing sound as it's coming out. Okay, so we never want to put our hand over that because steam is warmer than boiling water. So that temperature is above the boiling point, so it's hot. Also, what that means is there's a lot of gases that are inside these round bottom flask containers. So what I'm going to do is I'm going to cool this gas down quickly. As I cool it down, you're going to see something pretty cool take place. And what I've got in the beaker here to my left is some more water with some food coloring. And I put food coloring in there mainly so that you could see what's happening. So I'm going to cool this gas. As the gas gets cooled, something very, very cool is going to take place. I'm going to try to keep my hand out of the way so you can see what's happening here. I'm going to apologize in advance for the noise that it's about to make. Alright, so now what's happening is the gas is starting to cool. As a gas cools, it becomes compressed. As it's compressing, it starts to compress the other gases that are inside of the container. So it rapidly pulls the water in, causing a vacuum. And it's going to actually compress that gas so much that it's going to fill this container completely up with water. Here we go. Alright, so now what's happening is the gas is starting to cool. As a gas cools, it becomes compressed. As it's compressing, it starts to compress the other gases that are inside of the container. So it rapidly pulls the water in, causing a vacuum. And it's going to actually compress that gas so much that it's going to fill this container completely up with water. Now, if you've ever had a chemistry class, this is actually a temperature and a volume relationship. The bubble that's on top here, I don't know if you can see that bubble that's on top, that's the final volume of this gas. The gas used to be this same volume. Now, it's a bigger one. Kids usually like the bigger one anyway. So what I'm going to do is I'm going to pour this water back in there. I'm going to do it again with the big one. Now, since I've already preheated that, it's not going to take as long for it to heat back up. So as that's heating up, I start to see some steam coming out. Now it's spitting out already. We'll let it warm up a little bit. We'll give it a chance to let all the gases warm. Right now, boom, it's already going. So it did not take too long to get that water back into the phase where it needs to change from a liquid to a gas. Alright, so as that's building up pressure inside, we're going to cool the gas. As we cool a gas, it compresses. That's the same thing that happens if you were to, well, we all know about what happens if you leave a can of Coke in your car on a hot summer day. The pressure inside builds up and it explodes. Well, this is a reverse. This is an inversion. It's causing a pressure which is drawing everything inside that it can without collapsing the container. Now, if I cooled the gas down, it would suck air in, but that's no fun to watch. Alright, so let's get this guy. Okay. Alright, here we go. Let's turn the power off on that. Okay. So again, as that starts to cool within, I can see the water slowly lifting up. And now as it cools the gases inside, we see a tremendous, how quickly this gas changes or is compressed. And as it's compressed, it changes into a vacuum, drawing that liquid in quicker and quicker. Hopefully I'm not going to, oh, good. So it's going to try to draw it all in until that container is completely filled. Try to get my hand out of the way. Not pull it out of the liquid. Come on, get it in there. So still going, still going, still going, still going. It's trying to get it all. Ah, it's completely full. Okay. Alright, here we go. Let's turn the power off on that. Okay. So again, as that starts to cool within, I can see the water slowly lifting up. And now as it cools the gases inside, we see a tremendous, how quickly this gas changes or is compressed. And as it's compressed, it changes into a vacuum, drawing that liquid in quicker and quicker. Hopefully I'm not going to, oh, good. So it's going to try to draw it all in until that container is completely filled. Try to get my hand out of the way. And not pull it out of the liquid. Come on, get it in there. So still going, still going, still going, still going. It's trying to get it all. Ah, it's completely full. Must have been from the volume from the other container. Alright, so that concludes our demo for cooling of a gas. Pretty neat, huh?